Well, my name is Annabella Ferral. I work for the National Council of Scientific and Technical Research of Argentina and for Gulich Institute that belong to the National University of Córdoba and the National Commission for Space Activities, CONAE. I will talk about remote sensing experiences in monitoring land water quality indicator in central Argentina, a hyperspectral approach. Well, the outline of my presentation is first to introduce the workplace and work group, then the international, national, and local context in which we work, then the remote sensing of water quality, our methodological approach and guiding question. I will introduce some previous results regarding spatiotemporal analysis of an very eutrophic reservoir in our country, and our first results regarding hyperspectral analysis. And finally, I will mention some conclusions and future perspective. Well, my workplace is CONAE, the National Commission for Space Activity. It was created in 1991, and its mission is to propose and execute a strategic national space plan to achieve the socio-economical requirements of our country. I also belong to the National University of Córdoba, that it was founded in 1613. It has more than 120,000 students, 15 faculties, a lot of research centers, museums, hospitals, astronomical observatories, among other installations. So my institute is the Higher Space Studies Institute Mario Gulich. It works with a strong collaboration from Agencia Espacial Italiana. It belongs both to National University of Córdoba and CONAE, and its mission is to research, develop, and train human resources in remote sensing technologies applied to land, ocean, and atmosphere challenges. It aims to Pacific use. We work with in a very interdisciplinary way, and we like to transfer all the knowledge we generate jointly with other institutions. We have 2 master programs and 1 PhD program in space science, and we also give support to the various areas and projects of CONAE, as SAUCOM and SABIAMAR. The most important for us is to work with these values: quality, generosity, transparency, solidarity, and respect. Our work group is led by Dr. Escabuso, who is a physicist, is also the head of the institution at this moment. Well, I am a chemist, and I work in the development of environmental quality indicator and modeling from remote sensing and field data. Then it has Alba, who works in algae bloom models, Juliana, who works in snow pollution, Sofia in ecosystem service, Victor in hyperspectral analysis, Francisco also in hyperspectral laboratory measurements, and Matias Bonancea is a strong collaborator of us who works in another university, the Rio Cuarto University, and he's also from CONICET. All these boys and girls are doing the PhD in Gulich Institute. We also do this kind of activities in this group. We perform laboratory measurements. We go to the field to collect sample of snow, because we study also snow pollution or water quality, and we also process the satellite information. We work with other institutions and with several scientists, with the Provincial Administration of Hydric Research, and with the National Institute of Water, also with another institute from CONICET, and also from Brazil and Belgium. With these people, it's mentioned above. The international context in which we work is the Agenda 2030 of the Sustainable Development Goals. Now we are focused on number 6, clean water and sanitation, but we are also very committed with number 17, partnership for achieve the goals. And this is the reason for what we would like so much to collaborate in this GEO AquaWatch community. This agenda has some target, 167 specific indicator to be monitored. And so regarding the number 6, We are focused on the target number 6.3.2, that is to measure the proportion of water body with good ambient water quality. We would like to make map about the water quality of different reservoirs in Argentina and also in the region. We also work in a national context because we had a national space plan that is approved by the Congress of the Nation with 3 main lines: environmental, productive, and social. The environmental include water quality or water pollution and slow pollution, so we are focused in this, but also in the social one because the water quality is a matter of human health concern. Well, our local situation is that we have a reservoir which supply water to the second largest city in Argentina, which is located in the central of the country. This reservoir was built in 1888. It was the first artificial reservoir of the whole world, and now it's going through a severe phenomenon of eutrophication. So the government of Córdoba asked CONAE to evaluate San Roque water quality and eutrophication mitigation policies by remote sensing approach. So we would like to evaluate the mitigation policies, to study the impact of land use in the basin, to predict algae events, to detect the presence of toxic algae, to detect sources of contaminations, among other things. As you can see, this is a satellite images of 2004 where all the reservoir is going through a very severe bloom. So the San Roque Reservoir mitigation strategies were to build new wastewater treatment plant in the basin and to install an artificial aeration system in the reservoir. It was done in October 2008. As you can see, this is a line with diffuser with tubes that has holes and release bubbles of air. So it was installed in the deepest region of the reservoir to mitigate the proliferation of algae. The idea of this artificial aeration system is to break the thermocline in summer because this is a monomictic reservoir and in summer we have stratification events and the water of the surface cannot mix with the water of the bottom. So there is so much organic matter that aerobic bacteria start to oxidize all the organic matter in the bottom of the reservoir in the epolymium. And once the oxygen is consumed, the bacteria start to consume iron and manganese hydroxides, and when they reduce iron to iron 2 and manganese to manganese 2, the hydroxide don't stick anymore the phosphate. So the phosphate start to release from the sediments to the water body, and when the water body, the column of water mix again, we see tremendous eutrophication, tremendous blooms of algae. So with the artificial aeration system, we hope that the thermocline disappear, so we have oxygen in the whole water column, and in the bottom, the phosphate remain in the sediments. So we would see a good water quality in that region. Well, so the government asked us to study this. So the first question was, when a water body is considered eutrophic, because these were the first study of this kind in our province, and then if the artificial aeration system installing this in San Roque Reservoir delay or reduce the eutrophication process. So to say when it was eutrophic, we chose Carso Eutrophication Index. There are several indicators to study this. We chose Carso Eutrophication Index because it can be calculated from chlorophyll A that can be measured in the field and also from satellite. And then to answer the second question, we thought about how to see if the thermocline was present or not, so we could see the profile of temperature in the water column, the dissolved oxygen, the oxidation state of iron and manganese, the soluble reactive phosphorus in the hypolymium. But all these cannot be seen directly from remote sensing. But the spatial surface pattern of chlorophyll A and temperature can be seen by remote sensing and can be an indirect measurement of the stratification processes. So, to summarize, our methodological guiding question are, our methodology is to carry out field campaigns, to collect the data, to do it in simultaneous with the satellite path, to analyze satellite images, to develop semi-empirical model, to retrieve chlorophyll A and temperature, and to make a statistic over the data to study the temporal, spatial, and spectral patterns of our maps. So to answer the question, where are the pollution sources? Where are the risk zones? We should use very good spatial resolution satellite data. For example, from Landsat that has 30 meters or Sentinel-2 that has from 10 to 60 meters. Here we have example of a trophic state and thermal maps acquired during a bloom event in San Roque Reservoir. To answer the question, when does the bloom occur? How is the dynamic? Can we make forecast of this bloom? To study all this, we need temporal series with a very good temporal resolution, so we can use Terra or Aqua with MODIS sensor, Suomi MPP with BIRS sensor, GOES with AB sensor, or Sentinel-3 with OLCI sensor. Here we can see an example of a temporal series of chlorophyll A that is a daily temporal series. And to answer the question, what can we see from space? Can we detect specific pollutants? Can we detect, can we differentiate algae or cyanobacteria species? So for that, we need a very good spectral resolution because we need to understand the chemistry of the problem. And so we can use PRISMA from AC, ENMAD from DLR, or PACE from NASA that is going to be launched soon. So the monitoring plan of the reservoir was implemented in 2008 at the beginning monthly and now seasonally. We have 8 sampling points. The Provincial Hydric Resource Administration organized the sampling, and we try to schedule it with them with the path of some satellite of interest. We measure some variables as a profile, for example, temperature or pH or conductivity, and another variables are measured from samples that are taken in the reservoir and analyzed in a laboratory as chlorophyll A or a phytoplankton recount. Here we can see some results. For example, the marginal statistic field data for 3 years of field data. We can see in the y-axis the sites, sampling sites, and in the x-axis the value of different variables of temperatures, chlorophyll A, total phosphate, Secchi depth, among others. We can see the box plot, and we can see that based on in situ data, there is no significant difference between artificial sites and other sites. The red arrows are indicating the sites located over the artificial aeration zones. Then we wanted to see the temporal behavior of a variable. So we chose one sampling point, for example, the center of the reservoir, and we can see here a temporal series of 3 years of data for temperature, chlorophyll, or total phosphate, among others. We see a very perfect periodic behavior for temperature, that is an abiotic factor, but we see a seasonal behavior, but not perfect for the biotic variables as chlorophyll A, for example, or total phosphate, that is depend on the phytoplankton development also. You can see a huge variability inside an year for this latitude, and so we wanted to see the variability during one day, because in a boat. We are measuring during one day and we last more or less 6 hours. So here we can see from 11 until 3 p.m. what's happening with the chlorophyll A concentration in a site, and we see a lot of differences from 200 until 280 microgram per liter, and finally at 3 p.m. 120. And so it presents a very big daily circadian variability. Well, then we wanted to study the thermocline behavior because we wanted to see if the artificial aeration system was working properly. So we analyzed the thermocline frequency for different monitoring sites. For this, we analyzed the temperature against depth profiles, and the thermocline was defining when the jump in the temperature was almost 1 grade in 1 meter. Here we can see that the frequencies of thermocline for the site where the diffuser were installed were very little, were small. And we also saw that the chlorophyll A concentration for this site where the thermocline was absent, the chlorophyll A was less. So we could see that the stratification is very important, or the stratification make that chlorophyll A in the surface increase. It's bigger. Well, then we wanted to study by satellite information. So first we chose the NDVI index. This index allows to see the greenness in the water, and values greater than 0.1 can be classified as algae scum in the surface. So we plot here the NDVI against year for image of summer, acquired during the summer, and we can see in red the center of the reservoir behavior, and in black the artificial site behavior. The artificial aeration system was installed in 2008, and so after the diffuser installation was installed, the behavior were the opposite, and the zone with artificial aeration improved the water quality because decreased the NDVI. We performed a statistic test because each point was the average of 400 pixels in the lake surrounding the sampling point. We see always significant differences, except for 2 days, for example, during 2010 that was a very dry year. Well, from Landsat 5 we could develop a model for those years based on band blue, negative value, which means that absorb the chlorophyll A absorbing the blue, and the band 4, that is that algae reflect the light or scatter the light in the Near. This methodology allows us to detect the trophic level with a percentual error of 8%. And it was welcomed by the government since this satellite model did not overestimate trophic level. Sometimes subestimate, but never overestimate. Well, then we wanted to study the temporal behavior. Our lake is very small, so we chose a central pixel that was 250 meters. This is 1 kilometer pixel, but the one we chose is 250 meters because it's the band 1 and the band 2 of MODIS, the red and the Near, and we got a very good model with 0.78 square error. This is part of the thesis of Alba Germán, who works here in the Instituto Gulich and now is doing the PhD. It was possible to make a temporal series of chlorophyll A from that model, and we could see that the last 5 years presented an increase of chlorophyll A. So we make a student test, and we saw that this year showed significantly greater values of chlorophyll A than the previous years, the first years of the series. We also wanted to model the series but it has a very sinusoidal pattern or periodic pattern, not only with the frequencies of 1 year, but also with 6 months and also with 5 years near the Niño event, and 10 years that is related to the solar cycles. And so we use Hunt's algorithm based on harmonic function to model this series from 2001 until 2014. And we saw that during the 2010, the wastewater plant was installed in the main city of the San Roque watershed, that is here. And from this year, the quality of the water got worse. I'm sorry. So another thing we wanted to do was to say when our reservoir had a bloom. We tried to use Fick-Berholtz from the bibliography to say, for example, values greater than 100 microgram per liter is a bloom. But with that kind of methodology, our water was almost all the time in bloom. We used another approach to see exponential slopes, but the same we had all the year with bloom our reservoir. So we thought about a dynamic Berholtz. We had the model here, the model series. So we got the percentile 90 of that series, and we'll say, okay, when the value of chlorophyll is greater than the percentile 90 of the series, it will be a bloom. And we validated with Landsat and Sentinel data. And this is a work we published in the frame also of Alba Germán master and PhD thesis. And then this algorithm that you see here, this one, was implemented in Instituto Gulich in an operative way by the student of the master program. Alba coordinated these people, and so the student implemented, and we can see the Carson index online each day. And the National Institute of Water used this information to make monthly reports. Then, having a lot of years of data from Sentinel-2 and a resolution of 10 meters and 3 to 5 temporal resolution, we make a cube of data of more than 150 images of Sentinel-2 MCI. And we could evaluate the diffuser and wastewater plant impact on the water quality. Of course, the first we done was the model. Here we see the model with a square error of 0.77. We validated, and then we could study the impact of diffusers again. We could evaluate the spatial pattern of bloom occurrence. For example, we can see the percentage of bloom here. We can see all the statistics, spatial temporal statistic of the reservoir. Here we can see the slope of chlorophyll A for the whole cube of data that is increasing as an average, it's increasing in the north. And we also saw that in the center of the reservoir during winter, it is increasing the chlorophyll A values. It's like the background of the reservoir in winter is increasing. And this was published, and it was also developed in the frame of Alba Germán PhD thesis. And well, now I will talk about hyperspectral analysis. This is the vacancy area in Argentina. If we look in Scopus, in the title after non keywords, the words remote sensing, water quality, and hyperspectra, you only find 2 works for Argentina. In our region, Brazil is the leader, and in the world, China and United States, followed by Europe. The 2 works we found was, one was done with spectroradiometer, field spectroradiometer, and Sentinel and multispectral satellite data to retrieve chlorophyll A from a college that is Andrea Drott and Paula Tesanos, that are very good scientists. We know her, both women. And the second one is from us, from Victor Gauto. He went to Dr. Giardino laboratory in Italy to learn how to use Prisma data to study water quality. Now he's doing the PhD in the Gulich Institute. He studied the performance of Prisma and Sentinel-2 for different kind of type of waters, a very turbid one, a very productive one, and clean waters. And we saw that the performance of both sensors are very similar. With Prisma, we can see nice spectral signatures because it has 66 bands in this region, this near, and Sentinel has only 12, so it is very different the behavior. Well, 12 in total, less in the Disney. And so we also evaluate atmospheric correction algorithm, and we saw that are critical for clean water, but not critical at all for very turbid water. And well, this gives us some experience with hyperspectral information. We carry out a radiometric information, radiometric campaign in the San Roque Reservoir. This is an average of 25 spectral signatures for San Roque Reservoir. We can see this peak that is produced by algae or cyanobacteria in the surface, as you can see here. So we want to understand this kind of plot, and as a chemist, we say, okay, we will make some experiment in the laboratory. So we wanted to measure the behavior of algae and cyanobacteria. The first we found were cyanobacteria species that were cultured in Seprocor by Dr. Abelau's group. And we also meet with Dr. Burgos, that is a spectrometer, especially in spectroscopy, and Dr. Agimoni from Belgium, that is specialist in hyperspectral data, and well, Dr. Bonancia, who worked with us all the time. And so we performed this kind of experiment. We had pure culture concentration of microcystis to begin, of 10 to the 8 cell per liter. We made 5 dilutions in the laboratory with the media, specific media. And then we measured reflectance, absorbance, and fluorescence spectra for all the dilutions. As you can see, absorption and fluorescence are important to understand the reflectance spectra, and also the scattering process that I am not including this kind of measurement in this webinar. Here we can see the first result of absorption. We measured this in physical chemistry department of the National University of Córdoba and also in CONAE. These are results from dilutions, and you can see liquid sample, not in filters, but liquid sample. So we have a lot of effect of scattering. As you see, when you increase the algae in the dilution, the algae concentration, you have more and more scattering. So you have greater values that are, here it says absorbance, but is dispersion also. Here we are seeing absorbance plus dispersion or scattering. As you can see here, you increase the concentration and the peak increased linearly. We made then the analysis linearly with the concentration. And the square means the absorption of chlorophyll A. And the circles are the absorption features of phycocyanin. So we saw these typical features, and we look some reference values, and they are in accordance. Then we measure the fluorescence. As you see, the fluorescence spectra also increased linearly with the microcystis concentration and has different peaks. The excitation was in the blue, and the emission was measured from 500 to 800 nanometers. Here we have the correlation, the Pearson correlation coefficients, and the sensibility. What the meaning against the wavelength? What the meaning of correlation? Pearson is, for each wavelength we have 6 concentration of microcystis. So we make a plot of fluorescence against concentration, and we have a line with a Pearson correlation, and this is the number here. As you see, you increase the fluorescence, behave linearly with the concentrations. So you increase the concentration, and you increase and you have a very good correlation with the concentration for all wavelengths, except for some, you have a very good correlation. And the sensibility is the slope. Higher the slope, higher the sensibility. Of course, in the peaks are the higher sensibility. So if you want to measure chlorophyll A from microcystis, you should choose 680, that is the peak of chlorophyll A. Also, you have the peak of phycocyanin and the peak of chlorophyll B. Then we measure the reflectance curves in the laboratory with a field radiometer. We have this experimental setup. Francisco Nemiña helped us and is working in this moment, is preparing a work about all this measurement of reflectance. Here we have the sensor in the roof, the sample in the bottom, and halogen lamps, 45 degrees, illuminating the sample. And here are the results, for example, for the reflectance curve of microcystis. You have different concentrations. The nicest thing is here to see the fluorescence peak only for the dilute sample. The dilute microcystis show the fluorescence peak, and when you increase the concentration, the fluorescence peak disappears. It's swallowed by the absorption valley. And you also see the red shift in the near because of the absorption valley is increasing and the peak is shift. It shifts also almost 20 nanometers. So the band here of Sentinel of 705 nanometers with 10 nanometer width remain far from this peak for very concentrated microcystis. That is very important to take into account to deliver to analyze the algorithm performance, for example, of NDCI. Then you have in black lines and black solid lines the feature of absorption of chlorophyll A here and here, and the absorption feature of phycocyanin. Here you can see also. Well, we performed the reflectance spectrum for more cyanobacteria culture, Dolichospermum, Pseudonavaena, and Oscillatoria. We made the same a lot of dilutions. And here we see the performance for these are the reflectance spectral for Pseudonavaena, Oscillatoria, Dolichospermum, and microcystis. Here we see the correlation and sensibility plots. Something very curious is to see that Pseudonavaena and Oscillatoria presents a correlation coefficient negative for the wavelength where the chlorophyll A and phycocyanin absorb. And that is very interesting because it says that the absorption feature win the scattering features. In Dolichospermum and microcystis, the scattering processes do not allow to see the absorption feature as a negative correlation values. To understand this kind of plot, I thanks to Alexander Castaña, who helped me to interpret this. Well, the normalized reflectance spectra are shown here, but only for the vis near region, as you can see. And here we can see the difference in the shapes because we normalize the spectral by the maximum. And so we can see, for example, the fluorescence peak does not appear for Dolichospermum, or we can see that phycocyanin valley at 620 is shift to lower wavelength for Oscillatoria and microcystis, and slightly to greater one for Dolichospermum. This can be used maybe in the future to detect differences between cyanobacteria species. But to analyze better this, we use some spectral metrics. For example, the normalized spectral similarity index that is built by using the Euclidean distance between two vectors and the angle between two vectors. And we built this. The one who proposed it was Nimaduri in 2010. And this is the normalized spectral similarity index. The Euclidean distance is normalized by the biggest distance between all the series of data. And here you have as a minimum 0 and as a maximum square 2. And so here is plot the NS3, this metric, And we can see for all the different dilutions and all the dilution of cyanobacteria for the reflectance spectra. And we can see, for example, that some species differentiate depending on their concentration. For example, Oscillatoria concentrated has a fluorescent peak that is weak, does not differ from microcystis concentrated, where the fluorescent peak is absent. But it differs from microcystis dilute because the fluorescent peak is very defined. So this is very interesting things. Well, then we used to finalize some Prisma data. We chose a Prisma data acquired during a bloom event in San Roque Reservoir last year. Prisma has 66 bands in the Bisneer and 171 in the Swir and 30-meter resolution. We have to correct the georeferentiation in our latitudes. At the beginning, we wanted to make a mask with a water body, but we found a severe bloom. So we download some planet images to see if it was grass or was bloom. We couldn't define it. So we used the SWIR 2 micrometer band to that that is the near reflection of the algae, that is the absorption of phycocyanin, and then a chlorophyll proportional map, that is the same band but divided by 665, that is the absorption of chlorophyll A. Here we can see different patterns, more chlorophyll A in the reservoir than cyano index of phycocyanin. Then we made a PCI analysis over the lake for all the data, the cube for this SWIR cube. Here is the first component that is similar to the cyano index, as you see here, a similar pattern. Then a pattern that is similar to the whole water body, more water. And then a pattern that is spread with some points all over the reservoir. So we thought here as cyano presence, we put it in the green channel. Here as the water, the background of the reservoir, we put it in the blue. And here the other, maybe we think about another algae, we put it in the red because in our reservoir we also have brownish algae. We have field data from a previous day that was acquired the 8th of March, and the Prisma image was acquired the 11th of March, 3 days. We saw that there were no rainy events. The water was stable. And here we have the phytoplankton composition. And here we see more cyanobacteria than in the other side. This site is the center of the reservoir here, and this site is the north here. So we can see that this site, this and this are, as we saw, we think about cyano present here and here. And we took some spectral shapes, spectral vectors from the image, and we can see in the north the green behavior, and in the center the cyan behavior. We see a lot of signal in the SWIR because of the presence of CAMs in the water surface. So we have a lot of scattering. Although we have water, we have a big signal in the SWIR. And this is important to take into account when you perform link correction with severe algae bloom. And in the red here, more or less, in the number 3, we have this composition with Ceratium and Aulacauseria that are more brownish. And here we see it in the red, like a flat region, meaning that it's more reddish, that zone, and also the valley of absorption of chlorophyll A. And well, that is a way to understand the spectral behavior by analyzing also institute data. To finalize, we wanted to compare the spectra measured in the laboratory and the spectral measured by Prisma. So we resample the laboratory measurement to the, we make a convolution to have the Prisma response. And so we compare the, we made a spectral angle mapper classification by putting as end member the medium. The medium was the medium in the laboratory, almost transparent water, very dilute microcystin, 1 in 10, and microcystin very concentrated, and well, nothing. And so here we see all the places where we thought there were more water and some other species was defined as microcystin dilute, and the other as concentrated. Then we changed and we said, okay, our water body is not transparent water. So we took a sample from here, the blue one, from the reservoir. We took the number 2 sample, and we used it at end member, and we classify better, and a lot of part of the water body was classified as microcystic presence, and the other like as water. And we are continuing analyzing this kind of thing. We wanted to see, to show all the methodology we are using, and our future perspective is to work in the development of a geospatial system for the monitoring of the quality of inland water bodies destined for purification in Argentina. It is held by the National Institute of Water, and we are with Dr. Bonance and I and all our team. We are developing a model for different water bodies. Here we have an example for Rio Tercero, field measurements, and also radiometric measurement, for example, for that Salto Grande in Entre Rios. And to finalize, we wanted to say that Argentina is going to launch Sabiamar mission, that is the Argentine satellite based on environmental information from the sea. If we have a global scenario of 800 meter spatial resolution and a regional one for 200 meter spatial resolution for South American coast, we will have water leaving radiance, chlorophyll A, diffuse attenuation, PAR, and turbidity as the main products. Here are the bands of Sabiamar. She is Carolina Tauro. She belongs to CONAE, and CONAE is the PI of Sabiamar. I took this table from a presentation she made, and it's available here. I only translated to the English. And the conclusions regarding remote hyperspectral results mainly are that laboratory measurements show that the reflectance spectral and shapes of cyanobacteria cultures depend on cell concentrations, and this issue should be taken into account to develop robust remote sensing algorithms. That is the main conclusion. Then we can use different metrics to explore the separability of spectral. The chlorophyll fluorescent peak near 680 can be seen mainly for low concentration and is almost absent for Dolichospermus species. The PCI show very good performance to analyze this kind of water quality maps. And one of the main important, international cooperation is mandatory to improve our capability to explore and understand the complex spectral behavior of natural water bodies, among other conclusions. And so, to summarize, social equity and healthy environment, we should achieve to these things. And this is a picture of Antonio Berni. Is a very famous painter in Argentina. This is the Riachuelo. It's one of the most polluted rivers in the world that is in Buenos Aires. He's a boy that lived in poverty, and 60 years before he painted this, and nowadays we have the same problems in our country, and we think that satellite technology make visible all these problematics and help to stakeholders to mitigate the poverty and also the health environment. Well, some references. And I want to thank to GEO AquaWatch community for this opportunity, and special thanks to Alexander, Megan, and Mary for their support. And I want to thank here also to all the people who participate in this research, as I show some photograph before. And that is my email if somebody has any question. Thank you very much.